Hi everyone. Firstly, just apologies for the delay, just having a few technical issues, and that's all sorted now. Firstly, just like to thank everyone for joining the Mastermind. We've got a very exciting one today. So we have Pradeep, who is a software engineer working at Walmart Global. He's going to be walking us through some database stuff for your applications. So with no further waiting, please Pradeep, take us away.
All right, thank you, folks. Let me quickly share my screen. Okay, so we're going to talk about databases today. What I want to cover is a very bottoms-up approach to essentially enable everyone to choose how to go about choosing a database for your application. I have about 18 slides, so give or take like 2 to 3 minutes per slide. So it should be done in about 40 minutes. And then we can do a small exercise in the end and then have some time for Q&A. And if you want to interrupt me for Q&A, please shout out and then just interrupt me. And it's totally fine. And I can answer any questions in the middle. Let me know if I'm talking too fast. If I have to go slow, I'll go slow. If this is okay, then I will continue at this speed. Okay. So we'll start with essentially the mechanics of writing data on disk. How is it different from main memory? What's indexing? How do you do? I mean, how does indexing impact reads? How does indexing impact writes? Then we'll talk a little bit about concurrent operations on records, and then we'll talk kind of move on to scale and figure out how scale impacts concurrency, reads, and writes. We'll also look at transactions. Where does transactions come into play, and then how scale impacts transactions. And in the end, I'll give a simplified flowchart for choosing data stores with some vendors out there. And that could be a reference, and then you could use it as a starting point for all your database choices. And if time permits, we can do an optional exercise where we can map a particular use case and figure out for this use case, which data store or database should we go after. All right, cool. Okay, so let's talk about data writes on disks. So why do we write data on disk? We write data on disk primarily for durability. And what is the primary element or the primary, like the basic fundamental block of writing data on disk? Many of you might be familiar with this. It's what is known as a page. You can think of a page as the fundamental unit in which we can write data into disk very efficiently. Okay, and this page is nothing but a set of rows. Like it's more or less like a table for simplicity's sake. And each row on the disk will have what is known as an offset. So there is this is typically a hexadecimal digit, that the offset. And every disk starting from row 0 will have like offset 1, offset 2, offset 3, offset 4, offset 5, etc. So naturally, because of the arrangement of data as rows on a disk, it is extremely efficient if you're writing data sequentially on the disk, meaning you're writing data one row after another. But because you have this collective abstraction called page to enable you to combine or batch some of these writes into one page unit, you're very efficient if you're writing page after page sequentially. You can do random writes into a disk, but it's highly inefficient. Okay. What about data reads? Right. Again, data reads are sequential. So you read from offset 0, offset 1, offset 2, offset 3. It's very fast on SSDs, but it's a bit slower on HDDs. But the fundamental philosophy remains the same, that you read sequentially from disk. Okay. Now let's look at data in memory. Data in memory is volatile, we all know. I mean, it's not durable at all. However, memory offers something that the disk cannot, and that's speed, right? And why is this? It is because we have random writes in memory. Essentially, you don't have this sequential headache in memory. You can write extremely fast into any location in your random access memory, right? That's why it's called random access. And it's extremely flexible, meaning that you can store any type of object in this memory as long as it is converted to raw bytes, correct? And same with data reads, right? So data reads are again pointer based from random locations, extremely fast. So you don't have the sequential overhead at all in reads, right? So you have this extremely fast and volatile and flexible main memory, a very durable but sequential disk storage, and you obviously want to harness the best of both, right? We need both, and that's why you go for databases as opposed to just flat files, because with just flat files you're just having data on disk, right? So how do we harness both? We will look at this when we talk about indexes. Okay. Any questions till now? Okay, cool. So before we go into indexes, let's talk a little bit about reads. Okay. Just imagine a list of objects, like a sequential list, which is on disk, A1, A2, A3 to AN. Now let's say I have to search for A3. Okay. The simplest approach is do a linear search, meaning I look at every record, and the moment I see A3, I come back and say found, but it's brutally slow. Binary search, which most of you might know, is now it's going to take this linear time and then make it into a logarithmic search. But because this is happening on disk, right? I mean, think of like how do you do binary search? You have to essentially divide and conquer. You can do binary search in main memory because you have random access. On disk, you only have sequential access, right? So even if you want to apply a sophisticated algorithm on disk, it will still be very, very slow, right? So we need RAM to do very fast reads, very fast searches. However, we can't load all the data from disk to memory. It's way too expensive. So if I have 64 GB of data on disk, I can't afford to load 64 GB of data in memory, simply because I don't have 64 gigs memory. Usually I'll have 8 or 16 gigs memory, right? So it's way too expensive. You could think of ways of batching this process where I will only load 8 gigs in memory and keep the remaining in hard disk, but it is still a very inefficient process, right? So what we need is we need something in memory that doesn't take all of our records that are on the disk and load it into memory, but somehow we should be able to use the data on disk with something in memory. And that something is nothing but the index, right? So what is the index? Index is nothing but a pointer. It is a memory pointer which has a pointer which points to an offset on the disk that contains the data record. So in our previous example, if you have A1, A2, A3 on the disk, let's say you have an index A1, it will just have a pointer to the offset of A1 on the disk here, right? This offset can be either a memory offset or a disk offset, but in our case here, let's talk about the disk offset. So why is this important? I mean, I think this now it is sort of becoming clear, right? Because I can search efficiently. Once I have an index in memory, I need to just look up that index, which I can do using a random access, and I can employ all sophisticated algorithms to look up the index in memory. And once I have the index, all I need to look at the offset that it points to and then retrieve the data. Some of the common analogies that we find in common day-to-day life is in the dictionary word to page index that you find in dictionaries, and hence the common data structure name dictionary in Python and all that, right? So that's like a very basic introduction to what an index is, why is it important, and how it facilitates faster reads while still allowing you to keep your data on the disk and having this index in memory. Okay. Okay, so now we have to read, and which is the primary operation of any database. And when you're reading, you have primarily two kinds of lookups, right? One is a point lookup. What I mean by point lookup is I'm looking for a specific record. And then you have range lookups, wherein you are looking for a range of records, right? Typically, the range lookup is an SQL where clause, where you'd say, like, I want date, I want records for date between, today and the last month, something like that, right? These are the two primary types of reads that typically happen on databases. So point lookups are best served by what is known as an hash index, right? Hash index is just improvising on the index concept, wherein you take a record and then you hash the value of the record, and you will, when I say hash, you are applying a hash function, correct? And this could be any hash function in the computer science literature. You apply the hash function and you get a key, right? And imagine the entire main memory is accessed as is organized as a table, and then the key is nothing but a row in that table, right? Row index in that table. So you would say table of that key, that row is equal to the record offset, which is the offset of the record on the disk. Okay. Whenever I'm reading, all I have to do is read the key, and then I will get the record offset, and from that offset, I read the record. That's it. It's extremely fast because it's almost O of 1. It's constant complexity because all I'm doing is looking up a key in the main memory, which is constant time. I read an offset, and from the offset, I go to the disk, fetch that record, and then come back. In fact, the fetching of the record from the disk is what it takes so much time that your order of 1 complexity here doesn't really matter in the main memory, right? But it's still very fast. And this is how most of the data stores that are deployed for point lookup purposes, like Aerospike, Redis, etc., they essentially read data in this manner, right? Redis is an exception because Redis doesn't read from the disk; it reads from memory, maintains a copy in memory. That's an exception. But any other data store that offers you very fast lookups, it uses this approach. Was there a question?
No, sorry. There was just the audio was here was coming in.
Okay.
Twice.
Okay, cool. And then let's look at range lookups now. So range lookup, you're not doing a point-based lookup. You're looking for a range of values, right? If we employ a similar hash index, like if you have a similar table which has a table of indexes and each of them pointing to the record offset, I will have to do a range lookup based on a linear kind of speed, right? I have to go to record 1, look for all the records between record 1 and range 1, and then I have to look for all the records from range 1 to n, and that is extremely slow. So what's an alternative, right? For those of us like who have been through the data structures in computer science, like trees come to mind immediately, simply because trees give us a very fast alternative to this linear search for doing range-based queries. Why? Because trees are are organized in a way that all the records are made to fit in a logarithmic in the height of the tree, and the height of the tree when you apply the big O way of traversing the tree will offer you a logarithmic speed of getting to all the nodes, right? And this is especially true if the tree is very balanced. What does balanced mean? That you are not building like a single tree which has like root to node, like the entire length of the tree surpasses the number of records from root to node. You don't have a very long tree. Instead, you have like a shallow tree with the root and then the nodes getting distributed uniformly, right? Even if you were to arrange the indexes in this manner, one problem still remains. The index will grow linearly with number of records. What I mean here is, let's say I have 10,000 records on the disk. I still need 10,000 indexes to point to these 10,000 records, right? And this is okay when I have data that is like 1 terabyte, 2 terabytes, I'm sorry, like 10 gigabytes, 100 gigabytes, because I can still have memory in the RAM, which can grow. These days it's not unfathomable to have like 256 gigs memory in RAM. But what if my record goes to like terabytes of data, right? One machine having 10 terabytes of data, now I have 10 terabytes of records. I obviously cannot have 10 terabytes in memory. So how do we solve this? We can't store all records in memory. That was ruled out. Now we know that you can't store all indexes also in memory. So we need some sort of index optimization, right? What we need to do is we need to reduce the number of records in the index. When I say number of records in the index is, if I have 10,000 records on the disk, I cannot have 10,000 index pointers in main memory. But I still need to be able to do very fast range-based lookups, right? I still need to be able to do logarithmic speed range-based lookup without loading all the index pointers in memory and without loading all the records in memory. Okay, that's the constraint we have. So how do we do this? Can we even do a constant search? Can we improvise from logarithmic to constant? We can't. Simply because this is the best we can do if we need a range-based answer. We can't do point-based lookup, because if I have to do point-based, I'm only getting, when I do a query, I'm only getting one record. Whereas in a tree, if I do a range, I'm traversing the path of a tree, and when I traverse the path, I will get the records in that range. And this I can do in logarithmic speed, right? So what do? We go back to our roots of sorting and now figure out how can we apply divide and conquer to split the index between the disk and the memory, right? This is the only option we have. We essentially have the disk and we have the memory. Now we can't store the index completely in memory. Now what other option do I have? I have to somehow figure out how can I store the index on disk and also harness the power of memory to make extremely fast searches a reality. So we split the index. But how do we split the index? Is it like a 50-50 split or a 30-70 split or a 60-40 split? What do we do? So I think the ratio is not that important. What is important is that we have some percentage of index in memory, remaining percent on the disk. And once the memory is full, once we can no longer store any more indexes in memory, we merge this to the disk, sort of what you do in merge sort, right? If we do this, we have utilized the disk and the memory to its full potential, we are able to do logarithmic searches on range-based queries, right? So we have satisfied all our requirements. If we did this, how does reads work, right? How will we essentially look for a record? When we look for a record, obviously you need speed, so you look for the index in the main memory first. And if the index is not in main memory, then you have to pull the index from the disk because you have stored your part of your index on disk, right? Now, this is where you employ something like a Bloom filter, which is a probabilistic data structure that helps you check if the index is in memory very fast. It gives a very fast, if true or false, Boolean check whether my index is in memory. So that is what gives you the speed up when you want to do reads on this kind of index optimization, even though a bulk of your index is stored on disk. And this is typically employed by almost all new and popular databases. Okay. Any questions so far? Is this going okay, or am I too fast, too slow? Let me know if you need any. If you need me to slow down, I can slow down. So let's look at concurrent record operations. It is pretty common for an application to have multiple instances. So you have essentially applications running on multiple cloud instances. And each of these instances will typically perform operations on the database, on the record, and sometimes multitude of these instances will operate on the same record, right? Or it could also be multiple instances of the application from the same machine, which is what multi-threading is all about. So either be it a multi-threaded application or be it a horizontally scaled application, this is a pretty common thing. So what does this lead to? Let's take a scenario, right? I'm using thread as a as like an abstraction here. Thread could mean another machine also. Let's say a thread writes a record A is equal to 1 and immediately gets an acknowledgement back that this record has been written. Now thread 1 sends a read to read A. However, before that can happen, thread 2 writes A is equal to 2, okay, and gets an ACK. Now, after thread 2 has written A is equal to 2, the thread 1 read arrives and it reads A is equal to 2, whereas it was expecting A is equal to 1, right? So this leads to what is commonly known as data inconsistency. And there are many jargons for this. Stale reads, that's one terminology. And then I think inconsistent reads, weak consistency. There's a multitude of jargon to explain this, but fundamentally this is what it is. It is inconsistent. I read A is equal to, I read A after writing it. I could get 1, I could get 2, I could get 3, whatever the value is, depending on how the threading infrastructure of that particular server handling the write handles the situation, right? So obviously, there are cases where this is unacceptable. So you need to solve for this. And you solve for this by obtaining a lock on the record. It's not sufficient to just obtain a lock on the record. You also have to obtain a lock on the index, right? If you did obtain this lock, then you essentially make sure that only one operation succeeds at a time, and you don't have like the thread 1 write and the thread 1 read will still get A equals 1 and not A equals 2. However, as a consequence of this, your writes slow down, right? Because you're obtaining a lock, which means that you have to now wait for the lock to be released and all the race conditions to be resolved before the second write can happen. So this is what in common database parlance we refer to as weak consistency versus strong consistency balance, right? If you want integrity of data, you have to sacrifice speed, and vice versa. If you want speed, you can't have integrity of data. You can't have both. And this is what the CAP theorem, which is pretty well-known theorem in the database world, states that you can't have consistency and availability. You can have either or, right? This is just a simplified way of explaining the CAP theorem. Okay. Now let's look at scale and how scale impacts things. Right? We'll look at vertical versus horizontal scale. Vertical scale, everyone is most familiar, right? In today's world, it's not unusual to have like a 10 terabyte disk with 256 gigs memory in a single machine, right? And from the data that we have, we see that but for like a very short number of, use cases that requires petabytes of data, most of the data fits in within a few terabytes or a few hundred gigabytes, right? So for most of the use cases, your data will fit on one machine. It is perfectly viable to say that my database is just one machine. However, machines go down, right? You can't predict, especially in today's cloud infrastructure. You don't have control. You don't run your DCs. You don't have any control over the machines. So machines go down. And in some cases, data has grown to like exabytes and petabytes. And who knows? I mean, you might be running a startup that today is only doing a few hundred gigabytes, which tomorrow could scale overnight, and suddenly you're looking at like a petabyte scale, right? Just to give you some numbers, let's say you grew to something like 10 million DAUs, daily active users. Doing some simple math, over 3 years, if you just had 10 million DAUs over 3 years without any growth, you would be looking at 36 petabytes of data, which is naturally not going to fit on 1 or 2 machines. So horizontal scale becomes inevitable. Now imagine I have to do concurrent operations, and I have to do these concurrent operations on a horizontal scale, which means that the previous lock that I was obtaining to maintain integrity, that lock I now have to obtain not over just one record on one machine, but on multiple copies of that record on multiple machines, right? And previously, what we had was that we had the index lookup happening only on one machine, where you would look at the pointer location in the memory, and the offset would point to the data element on to the data record on that disk. Now, however, you have an additional hop or an additional logic required to figure out, oh, I have this cluster of 100 machines. Where on these 100 machines is my data, right? You have that complexity as well. So this essentially is what I kind of commonly refer to as database hell. When you have to handle concurrent operations at this enormous scale, you come to what I would characterize as a database hell. So obviously we don't want to be in this hell, right? You want to minimize the hellish aspects of database. Sorry, did someone have a question?
Oh no, sorry. I was just
okay. All right, cool. So how do we minimize database hell? We figure out what to reduce, right? And between reads and writes, What is extremely difficult to scale, as we saw, it is obviously the writes. Okay. So one radical concept could be, what the hell, I will just not scale writes. And somebody would say, oh, well, why not? Right? So for most applications, the read to write ratio is something like 7:3 or 8:2 or 9:1. There are some exceptions, like if you have continuous data coming from IoT devices, or if you have an application like Uber, where there are constant driver updates, or you're in a multiplayer gaming like scenario. I mean, though we could argue that a peer-to-peer architecture could eliminate the need for multiple writes on a DB, but I mean, this is like a common write-heavy scenario, right? But for these exceptions, we figure out how to scale only reads, and we just do not scale writes at all. That's a perfectly viable option, because your reads are going anywhere from 100K RPS to like 1 million RPS, and this is typical of almost all large scale use cases, right? So how do we do this? From the single machine where, let's say, I'm taking the writes, I will just spawn multiple copies, commonly known as read replicas. So I'll spawn multiple copies, which means that each copy server can now handle a specific set of reads. So I could apply some logic where I can say that from the write machine, I will make a copy of records 1 to 1,000 to machine 1, make a copy of records 1,000 to 10,000 to machine 2, copy of records 10,000 to, I don't know, 1 million to machine 3, like some simple logic like that, right? And then all I need to do is, on whenever I get a read for the record 10,000, I should just have the intelligence to go to machine 3 where it is located. Okay, some simple logic like this works. So this is a compromise, obviously, right? This compromise is important because we can't forget concurrency, and concurrency comes into play when you have to scale writes, correct? For consistent reads, let's say I have to make my reads consistent, as seen in the last example. The latency will now become a function of all the copying that I have to do, correct? So if I write a record and then I immediately send an acknowledgement that this record is written, and forget about, I'll take care of the copying later, I will end up with inconsistent reads, like how we saw in the previous slides. So if I need consistent reads, I will have enormous latency, because my latency is now a function of waiting for all the copies to be successful. Only then the acknowledgement can go back, right? Whereas if I say I don't want consistent reads, my latency will be very fast. It is just a function of one write, and all the copies will be asynchronous. I don't have to wait until the copying is done. And hence you do this compromise, and this is what you commonly come to understand as strong consistency versus weak consistency in databases. And many databases, including Cassandra, allow you to tune this consistency level to say that I'm okay, I want low latency, weak, inconsistent reads. I'm okay with that. And the database will offer you that functionality. Or you can say, I'm not okay with this. I want strongly consistent, very consistent reads at the expense of a higher latency. And the database will allow you to do that. Okay. So you have to figure out what is the compromise that you need. Okay. So let's look a little bit at transactions. So what exactly is a transaction? I mean, transaction is again a very loosely used word, but typically when in the database world, when you refer to the word transactions, it means a two-phase commit. What does this mean? You essentially begin whenever you're making a transaction, you begin a lock, and this is a typical example, right? You subtract from record 1 and you add to record 2. So I'm paying someone money, money goes from my account, goes into someone else's account. And this has to happen in a lock, right? And then you commit this transaction, and once it is committed, you can release the lock. And this is what constitutes a transaction. Now imagine this transaction with concurrency and with scale. Okay. Now you'll enter a new realm of hell, because in all my previous cases, I was only looking at one single record. Now I have 2 records to look into, and the complexity between 1 and 2 increases exponentially as we add concurrency and as we add scale. Right. So in this case, you absolutely have to, I mean, my take is that you can avoid scale. Why? Because transactions are low in volume. Even on the most, I think, even on Visa, I think PayPal has something like 500 to 800 transactions per second at its peak. Whereas in your previous cases, we were looking at 100,000 plus kind of transactions for requests per second, right? And even Visa does something like 200 to 300 transactions per second. So these are not very high volume activities, and you can afford to do this in a single localized environment without having to do geo distribution. So you can essentially localize all your transactions and say, okay, you know what? I'm going to restrict transactions to one or 2 servers per region, right? And these transactions, they don't have to be distributed, they are localized. So for the entire population of India or US, I will have 10 such setups, and I will break my traffic into 10 distinct regions, and I will handle all these transactions locally. Okay. The concept of distributing transactions is extremely hard, because you have this 2-phase commit, and when you throw in geo distribution, which means that the copies of data are existing on multiple servers across the globe, you just need extremely complicated algorithms like Paxos and Raft, and even these things are not guaranteed to work all the time. So, I mean, distributed transactions is essentially best avoided until and unless you have absolutely, you find a use case where you cannot absolutely live without this distribution. Okay. So let's look at a simple flowchart, and I'll stop after this. So you start with the use case. You first ask, does my use case need support for 2-phase commit transactions? If the answer to that is yes, you just resort to RDBMS with either a single or 2 masters and multiple read replicas. This is typically what every company does. Every large company, whichever has to deal with transactions, this is the proven strategy to deploy. Now, let's say you don't have this transactions. Now you ask, okay, great. Can I tolerate stale reads? Stale reads is inconsistent reads, which is what we were looking at in the slides before. If the answer to that question is yes, the next question you ask is, do I need range-based queries or do I need only point lookups? So range-based queries are like, you could ask, okay, does this application need something like, if I have 5 columns in the database, do I need to retrieve just 1 record all the time? Or do I have use cases where I need to retrieve a set of records across rows and across columns? Typical SQL where clause. So if I have a where clause encompassing more than 1 columns, then the answer is yes, I need range-based queries. So if you need range-based queries, and if you can tolerate stale reads, and if you have enormous scale that the data cannot fit on one machine, you go with a distributed database which has a tree-like index, okay, which is typically Azure SQL, Cosmos, Cassandra, etc. Now, if the answer to that is no, if you want to do point-based lookups, you go with databases that have hash indexes. This is RocksDB, Redis, Aerospike, Couchbase. Any of these will do. Now, let's say I can't tolerate stale reads, so I want consistent reads. However, when you want consistent reads, one question you want to ask is, can I tolerate write latency? If someone says we can't tolerate the write latency, you discard that use case. Tell them this is simply not feasible to work out. And if you can, I mean, again, 500 milliseconds, I'm just using as a generic term, but you get the drift, right? Can I tolerate a little bit of higher latency? If the answer to that is yes, you can again go with a geo-distributed NoSQL data store, such as Cassandra, where Cassandra gives you options to tune the consistency level. And this sort of tuning is available even in Cosmos or in Couchbase and even in Aerospike. Okay. So this is like, I don't know, the simplest flowchart I could think of for figuring out what database I need to choose based on the characteristics of my use case. Okay. So it's 10:30. I think we are we have some more time left. Do you folks have any questions?
Yeah, I mean, I'm okay, keeping this going till, and if questions are exhausted, if you're okay with it, Pradeep,
Yeah, sure. So I'm done with my deck essentially. And I have one last use case if people are interested in figuring out how to do this. If people are not interested, I can stop here, or if you want me to do this simple exercise verbally, we can just walk through this.
Yeah, let's have this one, please.
Okay, all right. So let's say you have to store profile information for something like a FANG clone, like a Facebook clone, right? Typically, you'll have, let's say, 100 million DAUs. So how do you go about this, right? So what do you do? From 100 million DAUs, you figure out how much data I need to store, right? So what you need to figure out is how much data and what is the latency or slash throughput, right? So let's focus only on the data aspect, right? So 100, I think 10 million DAUs over 3 years translated to 36 petabytes. So 100 million will be around 360 petabytes. Okay, petabytes of data over 3 years. We use 3 years because you typically need to maintain this data for legal, etc., reasons. So this is a typical scale factor taken into consideration while scaling systems. So this is a lot of data, and profile information by nature. So I always want to go to my profile and do something with that profile, correct? From an application standpoint, it's a user trying to access the profile, which means it's a point-based lookup. However, I also have other consumers of profile data within my application. Like, for example, if you are Facebook, you would have, I don't know, a ton of analytics engines trying to fetch data from the profile store. Maybe not all of the data, but something like, I don't know, like age, to figure out age-related at targeting, just for argument's sake, right? So then you also need range-based lookups. So I need a point-based lookup, but I also need range-based lookups. So now there are two ways to look at this. So I'll say, okay, for point-based lookups, I will use a very fast point-based lookup data store. Like I'll go with Couchbase. And then I'll maintain a copy in a data store, which is optimized for range-based reads. In this case, it could be MS SQL or MySQL or Postgres. Or I can say I'll use a geo-distributed Cassandra Cosmos with weak consistency. Okay. Or I could say, to hell with all this, I'm going to sacrifice some point-based lookup, latency. To save cost, I'm just going to use Cosmos. And I will now tune consistency for specific read characteristics, for specific reads. Okay. Again, this kind of analysis and choices becomes very straightforward if I know what are the types of lookups I'm going to be doing. Often what happens is we overlook this and then we just say, okay, I want weak consistency. I'll go with Cassandra. I want strong consistency. I'll go with RDBMS or some borderline random choice like that. What also happens is the vendors are also trying to influence these decisions. No matter what any vendor says, they want their product to be sold. So it is in their best interest to kind of make sure that their product gets deployed. So you go to any vendor and take any use case, they will make the use case fit for that database. Okay. So it's best to follow at least some ground level based, fundamentals based characteristics while choosing databases. And I find this sort of, what should I say, a decision tree quite helpful. And it gives me an unbiased kind of neutral way to look at database choices without getting swayed by vendor dynamics. Okay. So that's pretty much what I had. Let me know if you guys have any questions. I will stop.
Hey, Pradeep. Yeah.
Go ahead.
Yeah. More often than not, like most of the use cases will end up having both the lookups, right? Like it's not that common when we come across only one, either point-based lookup or range-based lookup, right? It's more of an and, right? Unless we have like extremely focused, narrow microservices.
Well, look at profile only, right? So in profile, the main use case is a point-based lookup. See, what is the customer impacting use case here? The customer impacting use case is a point-based lookup. Whereas the range-based lookups are mostly for analytical or internal purposes, right?
Or if we consider advertisers also as a customers, like the targeting there will include this, right?
Yes. Yeah. Yeah. Again, So if you look at targeting as your primary economy driver for the company, then you obviously want to have a separate system for at targeting And that's what I mean. So you figure out the arbitrage, right? So you can say that I will optimize my customers for point-based lookups, because without customers, there is no point running ads, correct? So to do that, my cost arbitrage lets me have a purpose-built database for point-based lookups. It can be Redis, it can be whatever, right? However, for range-based lookups, I will take a copy of this, and because it is also driving my company's economy, I don't have too much of a cost constraint. So I can play around with a multitude of these choices, and I can sort of live with two different database technologies serving two different use cases. However, if you don't have the cost arbitrage, then you have to make the and choice, like what you're saying.
True. Yeah.
And to make the and choice is where you start making compromises, right? So let's say you go with Cassandra, you can still do a point-based lookup in Cassandra. It'll be a bit slow. It won't be as fast as Redis.
Yeah.
Right. However, it's one database. I can do point-based. I can also do range-based, but range-based lookups again won't be as fast. The problem with so the problem with something like Cassandra for a range-based lookup is you have no control over data distribution, right? So if I did a range-based query and I'm expecting a low latency response, and if the data is distributed over multitude of regions, and my range has to cover region 1, region 2, and region 3, then your range query takes forever, right? So if I have to do efficient range queries, I need a distributed data store, which also gives me the ability to choose my distribution algorithm. So I should be able to say that for a specific type of range queries, I want to be able to do very fast range lookups. So I need custom sharding, correct? So if you go with, so what I mean is you can't optimize for both in the same database.
True. Yeah.
Makes sense. So you optimize,
Yep.
and again, optimization comes at a cost. So you can't say, I want to also optimize, but I don't want to spend money. That is not going to fly either.
Yeah, and there is also this features. Let's say it is actually point-based as of now, but let's say we are actually adding another feature to that same application,
which for whatever reason happens to be a range-based lookup.
Yes.
And now you can't say, I don't have money.
We can't implement that feature.
Yeah. We can't implement that feature, right? That's not going to fly.
I think Bello, you had your hand raised.
Yeah. Hi everyone. So my question is, could we also analyze the database for, say, an analytic startup or company like Google Analytics, that you track events, which is more write than read? So you are sending events and then you are saving. So you have similar like 100 million users, daily users, and also you are keeping the data for as long as the product is like maybe over a 10-year scale or what have you.
So what you're talking about is a write-heavy data use case, correct?
Yes, yeah, right.
Man, write-heavy use cases are tricky. So if you want, okay. So let's break down write-heavy use cases. Let's take Google Analytics, right? Can you afford to miss one write?
So okay, based off Google Analytics, you you decide on what event you want to track. So for instance, now let's say a scenario where you want to track say there's an event, you want to track daily user what's it called, daily number of clicks on say the login button and all of. So I mean, you shouldn't be inconsistent. It should be consistent, and then yeah, so you can get the accurate number of users on your platform at so time to so time.
Well, true. I mean, that is a quality of service that you're expecting. But what if one click goes missing? Is it the end of the world?
No.
Right. Are you promising any QoS to your end client saying that my application absolutely will grab each and every click on the application? No, right? You don't have any legal implication. You don't have any financial implication. So technically, you could afford to miss a few writes. So whereas what you really cannot miss is the service going down, right?
Okay.
What you cannot miss is 10 million users' data not being able to be recorded because your database is down or it's not able to handle the capacity or whatever, right? So what this means is that the availability of the database is far more important than the consistency of my writes in this particular use case. So what I do is I now make sure that my database is extremely reliable and guaranteed to be available for every one of my users every time. Okay. And it is with the conscience I'm doing that. By doing this, I know that I could potentially lose some of the events that could be coming to my data store. In this case, it could be click events or whatever. But that percentage loss will be so minor that I can live with it.
Okay.
But you can't, if you did the reverse, if you said, I want to preserve every write of every user, you could do that, but you will lose. You will preserve 100 writes of one user, but you would lose all the writes of another user simply because that database for that user was not at all available.
Okay, so you are saying it will boil down to a decision choosing consistency over availability or availability over consistency.
Correct.
Okay.
Yeah. And this is same for reads or writes. And it's just that reads are a little more complicated simply because for a read to happen, you should have written the data. Whereas for writes, you're most concerned about writing the data consistently. I mean, one implies the other. I mean, you can't really distinguish the two. So in my head, I mean, whether it is read level consistency or write level consistency, the same kind of thinking applies. Does that answer your question?
Right. Yeah, it does. Yeah, thank you.
Okay, cool. There's something on the chat. Sorry, let me see. Oh, okay, cool. That's it. Any other questions?
So I have two questions.
Sure.
One is maybe less serious than the other, but first off, are there? I mean, I've seen some standard bodies, some standards where you're comparing, particularly when it comes to queries, right? You want to test very complex queries. There are some standards out there that can compare, say, Redis versus, something that's, built on not just a database, but a distributed architecture like Hadoop, for example, right? Are there, how valuable are some of those frameworks and things like that when it comes to comparing databases in some sense, right? Because I've seen standards where they have say set 100 queries that look at all different some very complex queries that can take even hours to run, if depending on the infrastructure that you have obviously underlying. But are those type of frameworks useful, or do you think that starts to get that's only useful when you're comparing it from the point of view of some very large enterprise systems looking to do analytics and things like that, but outside of that it becomes a little too much for the task?
Well, I definitely wouldn't term them as useless. They certainly are useful, because at least it gives you a reference of, okay, how databases perform under a particular constraint. A query is nothing but a constraint, right? What these tests will tell you is, under the same constraint, under the same hardware, this is how a multitude of databases will perform, correct? And that is still useful because it still gives me a reference. I'm better than starting from scratch with this data point. What it doesn't give you is, how will this query, let's say this query Q running at latency L on database D, unless your query is going to be the same Q, if you make a choice of database D and expect latency L, it's not going to fly, right? So it's important to recognize the difference. It's okay to use a reference test to say, okay, this is my baseline. I don't know, today there are like 100 databases, right? Or maybe more. So I can use the baseline to sort of get a basic filter and then apply my use case based filtering on top of that. That's a very viable approach. There is also Kyle Jepsen. I don't know if you guys have heard about this. So Jepsen conducts pretty much a very rigorous test on every database, and they publish the results. And they look at various aspects like strong consistency, write latency, read latency, etc. Very comprehensive testing done. And that could become one of the reference tests to look for as a filter mechanism. Definitely useful. But will that be the filter for you to choose a data store? No.
No, fair enough. And while you were going through the transactions per second, I was thinking about at least prior to the merge, the 9 transactions per second that Ethereum allows on its, or not allows, but what happens on that blockchain. So I was wondering, all kind of joke aside, like in what context, should you really consider a distributed ledger, right? Like coming at
oh my gosh.
I know it's a very it's almost a question in jest, but not really, right? Like there are some situations in which you're okay with that, right? But there's not many that I can think of. What are your views on that?
Well, a distributed ledger, like I said, right? I mean, if we go back to the consistency and scale database hell, now we are looking at, if you look at a transaction, now here, okay, where's my transaction slide? Yes. So here, this whole block, I'm assuming that this is a legit transaction, right? Because it is happening through there is no element of mistrust here, correct? Because it is a central transaction still. It is happening centrally. Whereas now, if I take out the trust element and I say that this subtract from record 1 and add to record 2, this itself, this 2 steps will now become, I don't know, 100 steps.
Yeah.
Depending on the chain of approvals. Now, which is why the transactions are on distributed ledgers are so slow, and whoever says that, you know, faster compute or some other magical thing will solve this, no, it's not going to solve. Simply because for this simple operation, I need
There's a
100
process involved for every transaction, right? That's
correct.
That's really what adds the latency.
Yeah, and think of it like this, right? Between the subtract from record 1 and add to record 2, there is verifications 1 to 100. I don't know, just using 100 as a number. And then there is one more verification here. And all of these now have to be.
And after that's all done, you have to still, you know, add to the main ledger, right? Like it's not something that stops. Everyone's ledgers have to be updated. You know?
Correct. That verifications, that 1 to 100, right? This itself is like, you don't know where is 1, where is 99, where is 98. It could be 1 could be in New York, 99 could be in India, you know, 98 can be in I don't know, Antarctica. Who knows where the node, which is supposed to verify this transaction, where is that node? You can't even optimize it, correct? That's why it takes so much time.
There's of course some nuances, right? Like I think it's certain percentage have to agree, right? So it's
well,
not,
yeah. I'm taking 1 to 100 as the percentage, right? I mean, there will be like a few 100,000 nodes, and not all of them will verify.
Yeah. No, so there, I mean, the reason I asked that question though is, I mean, the question itself wasn't just, but the implication really of this is, you know, there are really very few common use cases that I think you should sort of very seriously look at it for, right? Like at least those that come to mind.
Oh, absolutely. Very few. You wouldn't look for a distributed ledger unless there is a transaction involved, unless there is a distributed transaction.
And unless
I wouldn't even call it a distributed transaction.
Parties and things like that, right? Like because it's over the last, particularly not recently, not in 2022, but prior to that, like, you know, everyone was looking at it for almost everything, right? There was a period of time, and that just was clearly nonsensical to probably somebody in your position, right? I think. What would you say is a very legitimate use case for it? You know.
I mean, outside, so it's hard to come up with a legitimate use case, right? So I think outside the world of, let's say, currencies, let's say that a currency is the most legit use case for a distributed ledger, right? Now, if I take out, can I even take out the currency aspect? In my head, you can't take out the currency aspect. Let's say, for example, you want to make, I think one of the use cases was land records, right? Land record ownership. Let's say I want to put it on a distributed ledger from a centralized council or whatever is that governing body that owns it, right? Now imagine the complexity of doing this, right? And if you want to do this without a currency element, how will you even do this? So let's apply some basic economics, right? The the land records are maintained in some system, some centralized system, which is paid for by the tax money of users, right? Of citizens. That is, there is some convoluted path of how a percentage of the tax money comes and funds this infrastructure that houses these land records. And now you're saying, I'm going to take this infrastructure and I'm going to distribute this infrastructure across the globe in a distributed ledger. Why? Because I don't trust the council or the central authority, whichever holds it. They could tamper with it, they could create copies, they could do whatever they want, right? Okay, valid argument. But now who's going to fund this? Because the who's going to fund this becomes important, because this is inherently going to be an anonymous distributed verification system where anyone on the globe who has who is a valid verifier or an approver in the form of a node can approve the legitimacy of these land records, right? So how are you going to fund it? You can't fund it without a basic element of economics built into the verification itself, right? If you don't do that, then you will have to figure out another convoluted, elaborate scheme to fund whoever is verifying the transaction. Now, if you conjure up another elaborate scheme, then you become another centralized entity, which is again prone to all the inefficiencies that you wanted to get rid of in the first place, right? So if you want to take any centralized transaction, in this case, I'm saying even the land record is a transaction, right? It is essentially a buy and sell. Somebody is transferring the land record to someone else. Without the currency aspect, it becomes almost impossible to do on a distributed ledger. Now, once you bring in the currency aspect, it becomes another currency.
Yeah.
Does that make sense?
Yeah, it does. I mean, I think there's fundamental challenges there, but I think in terms of if you take out the pure economic side of it, even if you look at it purely from the use cases, assuming you can solve the economics problem, it still needs a use cases where transaction volume isn't necessarily, at least at this stage, at least given today's, compute. I mean, frankly speaking, even if compute scales much more, you still run up against some fundamental math issues. But essentially, even if assuming it does get better, I think at least in the near term, it's the transaction volumes per minute per second transaction volumes have to be relatively low, right?
That's right. That's why I took the land record as an example, because it is a fairly low latency transaction.
High value transactions, but
it can be very high value. Yeah. Like it could be $1 million per transaction.
Yeah.
But you can't have 1 million transactions of $1, right?
Yeah. So that's fundamentally where one way of thinking about it. But even if you do solve for that, the economic aspect is still unresolved at some level.
Correct.
Yeah.
All right. I think we have overshot the time.
This was very, very good. Thank you, Pradeep.
Very cool.
For your time.
This was super. I had fun. This was a good session.
And regardless of all the LinkedIn issues, I actually figured out finally what they were. Switch it again.
What's an event without glitches?
Yeah. Yeah, but no, I appreciate you joining. We will be sharing like a post-produced video of this both on LinkedIn, YouTube. So feel free to, if there's any questions, anything that that people have, feel free to ask between now and then as well. We can definitely keep the interaction going on LinkedIn.
Sure, absolutely. Feel free to reach out to me. I am P Banavara on Twitter.
Thank you so much, Pradeep. We'll share that as well when we share the feeds out of the recording.
Awesome. Okay. Wonderful. Thank you, folks. Great chatting.
Bye.
Cheers. Bye-bye.
Hello, everyone, and thank you for getting this far. If you like this talk, please subscribe to our YouTube channel by clicking on the subscribe button on this page. If you would like to be a part of future events, particularly the live events, then please head to our LinkedIn channel, the URL for which will appear on this page as well. We've also added the URL to the comment section below. This Engineering Mastermind series is brought to you by Archimedes. Archimedes is a curated global software engineering guild. Archimedes believes that the future of work is here, and it goes well beyond remote work. The zenith of industrial age work was reached at the end of the 1990s and culminated with large multinational corporations around which most knowledge work was organized. Archimedes believes that the best way forward in the information age is a return to the not-so-distant past, where guilds and not companies were the dominant organizational entities around which work was facilitated. The Archimedes Guild is centered around software development and product development related skills. If you'd like to learn more about the Guild, please head to archimedes.dev. There you can learn more about what the Guild stands for, how the Guild is organized, and how you can engage with the Guild if you're interested in working either on a full-time, fractional, or a consulting basis with the type of talent that you see in these masterminds. Thank you for your time, and please remember to hit the subscribe button. Thank you.